Hello, sir. How are you
Yeah.
doing?
Good. How are you? Hey,
I'm good,
Dan.
sir.
Hey, great. Do you do you want to discuss anything?
Yes, sir. I've had a doubt. I've gone through
Yeah. Don't
the
hesitate.
multi-layer perceptron, but
Go ahead.
I was thinking, why did we choose our hidden layer D to be 7? Is there any particular reason for it?
Not really. It's more of a starting point.
Oh, got it, sir.
Yeah.
Yeah, I was just thinking
Yeah.
about it all the time. I was not
hmm
sure why it was 7.
As for neural network, uh, as for neural network, there is a lot of experimentation. With any new data set, you never know what might be the best number. You can, for every problem, you can almost go to the extreme of doing a grid search,
Yes,
and
sir.
this is a hyperparameter. But in terms of applying multi-layer perceptron model, generally, if you only have one layer, the size of that layer would almost uh, would, would almost be impossible to be bigger than the size of the data set, typically.
Yeah,
So
correct.
let's say you have 100 columns as the input variables, you would have fewer than 100 units, you know,
Right.
because some of these variables are not important. So the dimensions is reduced over time. If you have more than one layer, you can imagine the size of the layer become smaller as you go deeper into the network. So that's a convention, and that convention is, I think, because of the experimentation, and people found that this might be the optimal way of structuring. As for the exact number, you can change. You can try different things, but the general structure is like that. It's like a pyramid put on the side, if you
Yeah.
will. Yeah.
So if I add another hidden layer, so it's going to be less than 7. If I wanted to add another
Yeah.
hidden layer.
Yeah.
Got it.
For MLP, yes.
Yes, got it, sir. And I had another doubt. So you said we're not doing one hot encoder for our target variable because we need to have our the 0 and 1 the indexing to be ordered, right? So because our output is going to be ordered, right?
Uh, uh, let's see. You said the target variable has to be what?
You said in the demo.
Right.
You said, and it makes sense because you said we are not going to do one hot encoder. We're not going to do
One
one hot
hot.
and
Okay.
yeah,
Right.
right, because the output is going to be ordered, is going to be 0 1, and then we want the indexes to be ordered in that sense, 0
Right.
1,
Right.
right?
Right.
So
Right.
what struck me was, what if my target variable is an unordered target variable? So what if my target variable is the marital status, which has got single, married, divorced, unknown, etc., etc.? So in
Yeah.
that
Yeah.
case,
Yeah.
what do we do?
That's a good question. Um, I think probably you're more progressed than other of your classmates. Um, I can say this to you, but I think as for in front of the class, I would delay talking about this after today. I think
Sure, sir.
after today, it's better to put things in context. I can refer to things that I've already talked about. But a quick question is, it's okay for unordered labels of the target if the target is multi-class, and the labels, the meaning of the labels or the value of the labels does not mean that they have better or worse.
Yep.
It doesn't
Yes,
have
sir.
those meaning.
Yep.
So, but somehow it has to be ordered as well to make it work, right?
Yep. Yes. Yeah.
So the
That's why.
key is how you order them.
Yep.
In terms of applying data science, a convenient way would be to order them by their label, alphanumeric order.
Okay.
And this is why the one hot encoder orders that by default,
Yes, sir.
right? So if you use one hot encoder, I mean, no, you don't use one-hot encoder, but you use get dummies. But
Get dummies.
the
Yes.
logic is right. The
Right.
logic is the same. When the get dummies create column labels and decide to discard the first is the one that ranks the first in terms of the alphanumeric label,
Yeah.
right? So that is automatically dropped. And what is ranked first in the remaining labels are those that float up in terms of the sort order of the label. So this is the most convenient way to pre-process the Y. So based on this, you use this Y to train a model, and you will have as many nodes in the output layer as the number of columns of Y, right?
Right, sir.
As the number of levels of one. So in that order, the output nodes, each of them correspond to the same position outcome. So in that sense, if let's say divorce may be the first, right? It's D. Let's say divorce is a label, but it's not dropped. So
Yeah.
it's the first of the remaining labels. No, sorry, for output, sorry, for target, we don't drop it.
Yeah, we
I
did
almost
not drop.
forget that. We
Yeah, I
don't
was
drop
just
it.
thinking that.
So
Yeah.
divorce is the first
Yeah.
because it's D. Now, in the target, let's see, in the Y data, the flag variable for divorce is the first column. This will decide the first unit in the output layer is trying to predict divorce. So you can think of a corresponding position or index in the output layer is according to the way you sort the columns of the Y. So this order is arbitrary, but it doesn't affect the model. It doesn't
Yeah.
affect the performance of the model. This
Yes,
is
sir.
just by convenience. You just want to make sure that when you perform one-hot encoding for Y, the labels are indeed sorted by the alphanumeric order, so that when you diagnose the model, sometimes you want to go back and take a look at the weights. Then, because the structure is so complex, you want to be precise. You want to know precisely which unit in the output layer is trying to predict which label. This is super important. Otherwise, it will lead to errors in terms of interpreting the coefficients.
Yes, got it.
Right. And with two columns, it's much easier, right? It's much
Yeah.
less likely to make some
Yes.
mistakes.
Yes.
With multi-labels, you need to be careful, but you can do it. Follow the same procedure.
Yes, sir.
Yeah. Hello, everyone. I have not yet. Let me put on my face and you also do that if you can. So I haven't gone through all of the homework 2 yet. Ooh, Stravan. I mean, how do you get it upside down?
I do not know, Professor. I just
I guess probably you're using a pad.
no, no, I'm using my
No?
personal computer. I just tried to change the virtual background, but it just flips my
Okay.
image.
So maybe there's
I'm
a
trying to fix it.
filter
Yeah.
that put it.
In the video settings, there's something called rotate 90 degrees, so you can rotate your camera.
Okay.
Rotate camera?
Okay. Yeah, got it. Yeah.
Pretty
Yeah,
complex.
got it. Yeah, thank you.
Great. Now, as I was saying, I haven't gone through all of the homework 2, but is there any questions? Is there anything to discuss?
I have a question for homework.
So is that specific question? Is a hands-on question?
I think.
Okay. I'm planning to do Q&A demos, I think I will reserve that second half of the 3 hours time for that. I'm trying to get a sense of how much is it needed. Dan, you have a question about hands-on. So I'm imagining, because midterm is next week, you'll probably have, you're probably nervous in some areas of data pre-processing, data science, warm-up skills, or EDA, or things like that. If you have very specific questions, that's great. So that in the second half, once we finish off the first part of the neural network, and once I talk about the overview of the, somebody has a question? No? Okay. Once I go through the high level review of hey Justin, high level review of the midterm, then I'll open the time for very specific questions. I guess if you have questions, mostly they are about hands-on. It could be about the model implementation process, or it could be the pre-processing data. So the best way we can use the time is that you have a very specific question. I can do some demo live on my Jupyter notebook so that we can go deeper and I can explain things. There's infinite dimension that you can go in terms of understanding pandas or numpys, and also the processes of model building. But I simply don't have that time to make those videos. And I don't know, I don't assume, maybe you know it, who knows? So I don't have to explain them. But if you do have a question, and if the question is shared by many students, then it's best that I do some demo. So that's my plan. Sounds good. If it's good, thumb up. I can get a sense of the demand. So basically, I'm thinking of using the time left of this class, today's class, after I talk about neural network, to do live demos of hands-on based on your questions. But if you don't have questions, then I guess we can't do any meaningful demo. Sum up in the comment, in Zoom, if you think that's a good idea, maybe get a sense of how much time I need to reserve from, when do I stop talking about neural network? Neural network is not covered, is not part of homework, no, it's homework 3. It's not part of the first exam. So just one thumb up. So I guess it's not very, okay, 3, 4, great. 3, 4, 3, 4, okay. 5, perfect, thank you. Does it automatically disappear without you clicking no? Or does it, like, if you click yes, it shows up for 3 seconds and it's gone? Or, I have a party, so let's have a party. I want a party, but I have things to do. Anyway, so let's plan for that. Because of this, now you can kind of think of when I was talking about things, if you already previewed this chapter and you kind of know what I'm talking about, then think about what question you want to ask, by the end of the class. Not by the end, but by the end of me talking about neural networks. Okay. So let's get started. Good evening. It's a beautiful day. Beautiful day. Can't be better, right? So let me share my screen. Wait, hold on. 1 second. Oh, by the way, do all of you have a camera, right? During the exam, I would require you to show your face. During the exam, not today. But let's do a test run. Put on the video if you can. Thumb up. Right. I'm still waiting. Sabine. Soya, I saw you before, so you're fine. And Ifraz. Ifraz. Can you turn on? Oh yeah, I saw. Great. So, next week, during the course of the entire exam, you need to put on your camera, turn on your camera. All right. So let's get started. Share my screen. Any questions before we start? Oh, yeah. Co-host. Almost forget. Where are you? Okay. Thank you. Oh, by the way, last time the meeting was interrupted, I was dropped out. And it turns out the video was saved. So if you saw the lecture, yeah, so Zoom is pretty good, and easy to use, much easier to use. So it's already included in the lecture video. Share screen. Can you see that? Can you see the slideshow?
Yes.
Yeah, great. So I will not review previous chapter, but there are things that will be repeated here because of the connection between logistic regression or Adaline model with neural networks. I think for most of you, probably this point is not clear, or even you may not be aware. But after this class, I hope this point is very clear and loud. Logistic regression is a building block of neural networks. If you understand logistic regression, the in and out, if you understand logistic regression as if it's a toy that you have played with, so that you can take it apart and put together without your eyes open, then from logistic regression to neural networks, it's not going to be a problem. There will be new things. There will be, new things introduced, mean batch gradient descent, and other alternative activation functions. But those only affect part of the process. If you replace those processes, the entire architecture doesn't change. So the entire process flow doesn't change. The most important thing is, understand the basic blocks of things. Forward prop, backward prop. For neural networks, it's the relationship between the hidden layers. That's the most challenging and most complex aspects of neural network. So this is not for agenda for today. We can't do everything here. This is the agenda for the third module. And I'll follow a similar flow as I talked about Adaline model and logistic regression. So I'll do some intro, sort of the conceptual level. What is it? How is it connected to logistic regression? That gives you an entry point to for better perspective of seeing this new thing. What is new thing? What is really new here? Turns out it's not much more. A lot of things you're already familiar. If you have done homework 1 and 2, I heard, I got some feedback from some of you saying homework 2 is really helpful. to understand what is logistic regression. You know, if you feel good about that, then I wouldn't imagine you have too much of a trouble. There will be some complexity here. There will be some new processes here, but the jump is not much of a difficulty level as before. So I'll talk about conceptual, then quickly I'll transition to the process. Again, you know, take it apart, talk about one loop. And as for the logistic regression or the perceptual learning rule, it's forward and backward. That's one loop, forward and backward. Forward remains straightforward. Backward is much more complex. We'll talk about those. I'll also talk about intuitions of why does it happen this way? What's the necessity, or what's the meaning of the additional steps? Then after being able to train neural network, you'll notice a difference. The time that's needed to train the same data set will increase from logistic regression to neural network if you have a larger layer. And then based on that basic implementation, we'll implement several new improvements, talk about several new concepts. And in the end of this module, we'll use the open source libraries, you know, because that's the ultimate practices. Programming these is a way to help you understand them. The purpose is not to use these. You can, but you know that you're losing time. You're incurring the cost of running models and running the training on codes that are built up in a way that's not efficient. This way of coding the neural network model is not efficient, especially if you increase the layers, because we are using Python codes instead of using leveraging the C++ codes. Those packages leverage better, more efficient code foundations. So better to use those, as well as less likely to make any mistake. You know, how much time on average does it require you to solve a bug? Half a day, maybe? Or some of the tough bugs maybe may take you 3 days. Sometimes it took me 1 day. So it's counterproductive. And these packages are very robust. Once you understand how to use them, you know, you can play with them much faster and be able to do a lot of things. Because our focus is applications. We're not trying to do research on the algorithm itself. You know, I'm here to help you understand the features, the limits, the strength, and the most important is how to use them quickly. Good? Make sense? Now, some terminologies, don't be afraid. You know, you don't have to read it now, but we can come back if we need. Some of these, a lot of these are already, you're already familiar, including regularization. And this is just a way to put it in the context of neural network. Because of the change of structure for neural network, some of the concepts or some of the implementations of these, implementation of some of these will be changed. For instance, the weight used to be vector. Now it's a matrix. There are 2 matrices for a 3-layer MLP. As versus previously, there's only 1 weight vector. Previously, the bias is included in the weight vector. There's only 1 bias of the output unit. Now there are 2 sets of biases, and in each set of bias there are multiple items. So we have 2 bias vectors instead of only 1 bias element. So that's big changes. And these changes are because of the more complex structures of neural networks. That's the nature it is. We'll revisit gradient descent for 2 times, I think 3 times in the course of this module. I will unfold what goes, what do we go through when we do the gradient descent for the output layer and the hidden layer. That's the first time we'll talk about this. One of the most complex differences in neural network is the process of gradient descent because of the multiple layers. The second time we'll deal with that is the mini batch gradient descent. It increases the learning efficiency. It get rid of the oscillation during the learning. You see it very clearly when you watch the videos. And in class demo, I also show that. That's the second time. The third time, we'll make some modifications in gradient descent is when we introduce new alternative activation functions. And recall that gradient descent is all about those nonlinear activation functions that makes gradient descent complex, because there are derivatives, partial derivatives to be made, and every time an activation function is changed, this form sometimes go through radical changes. You have to know the background, linear algebra to be able to fully understand them. But of course, you can find materials to tell you exactly what to change, and depends on at what level you want to understand these. So we'll revisit that 3 times. Regularization, same concept. And agenda for today, I will only talk until this point. But in fact, since we will reserve some time for the Q&A, I may not even get to here. We'll see. I'm planning on using an hour to talk about all of these, and then we'll kind of stop at there. Whichever point I finished, and we'll open the questions. Sounds good? I will review Q&A, I will review midterm exam at the end by the time we hit the 1 hour time point. So let me set a timer. Okay. All right. So a brief intro of multi-layer perceptron, and this is something we'll do. So neural networks. So we're talking about neural networks. NN is the acronym. And now we're talking about multi-layer perceptron to begin with. MLP is the acronym. Why do we talk about this? Notice that perceptron is mentioned before in the second module. We call them artificial neuron, or a single neuron, artificial neuron, perceptron neuron, perceptron learning rule, or a perceptron model, a single perceptron model. And the difference is that now we have multi-layer. Does it mean that we didn't have multi-layer? Not really. Depends on how you look at it. You can say we only had 1 layer because it's single neuron, or we didn't even have a layer per se. We just have a neuron. But they actually have 2 layers if you look at them from the perspective of neural networks. So the perspective changes how you say it. Neither is wrong, or neither is definitely correct. There's not really, you can describe it both ways, just from two perspectives. Let's see. So now let's do this. Let's do a fun discussion, or kind of thinking, reflection. So I talked about two things. Neural networks and multi-layer perceptron. And there's a larger circle, there's a smaller circle. One refers to one of these, the other refers to the other of these. Which one do you think is neural networks, and which one do you think is a multi-layer perceptron models? Both of them are referring to at least a range of things. None of these is a single or simple concept. Both of these represent a range of variations of models, but still you can say that one is a category of the other. So what do you think is a category of the other? What is a smaller circle and what is the larger circle? Feel free to talk. Feel free to, ask a follow-up question. Feel free to say any doubt.
The big
MLP
one
is a small circle.
no.
I think
Yeah.
a neural network is a big one.
And provide your reason. Why do you think that way?
Because neural network is the each of the branch or something has multi layers. So there are many should be the biggest one.
Sounds reasonable. And plus, probably neural network is cooler, so it deserves to be bigger. That's fair, but but I said that reason because it's cooler. Just kidding. Anyway, any other opinions or anyone agrees?
MLP is a type of neural network. The multi-layer perceptron is a type of neural network. Adaline model is a type of neural network. And logistic regression model is also a type of neural network.
Let me stop you there. Logistic regression, if you say it's a neural network, then much fewer people will agree with you. Although you can argue, right? You can argue, you can definitely have you can make a point. But still, yeah, so that part is, I like to correct that. But MLP, yes. So think about, other than Adaline and MLP, what other neural networks do you know or have you heard about? Or if you have played with, that's even better. What other neural networks can you, or types of neural network can you name? Anybody?
Deep neural networks?
Yeah, deep neural nets. Yes, a few, more specifically, types of deep nets, do you know? No?
No, sir.
Oh, yeah. So I think you have pretty good, I mean, all of you, pretty good sense about these differences. So let me begin with MLP. MLP is multi-layer. That is sort of a description, but P is really the keyword here. P is perceptron, right? Perceptron model. And strike that. Can't even do that. Okay. So T is perceptron. And what is a perceptron? It's a perceptron learning rule. It comes from that. So in a way, MLP is the next step of perceptron learning rule, or you can say Adaline or logistic regression. So each of these is replaced by that, and the next step becomes MLP. So MLP, so that's why, and MLP is part of the neural network, and logistic regression is the sort of the precursor of MLP, and that's why understanding logistic regression as well as these basic neurons will be helpful to understand MLP. So, coming from the beginning of this course, at least you have some familiarity to imagine how this is created. But then neural networks have other kinds, Scary. Looks like anyway. That's fun. Anyway, so there are different kinds of neural networks. There are deep nets. There are weird names, residual neural networks. There are LSTM, stands for something like long, short-term, something. It's kind of part of the RNN, I think. You have CNN, convolutional neural networks. The book, by the way, talks about all of these, so you can quickly dive into those very quickly. So just a high-level overview of where MLP is and why do we call them neural networks, because it's a kind of neural. It's perhaps the most basic form of neural networks. Even though it's single neuron, it has two layers. It has an input layer, it has input layer, it has an output layer. And in fact, the output layer is considered the entire part here, even with the weights. So basically it's all of it. And the input layer is just the inputs. This is the bias. Or this is not really the bias, but it's the bias term, which is 0. Anyway, so this is the bias. So it does have two layers if you think about it as a kind of neural network. And the most fundamental things going on here is in the output layer, or we can say it's the output unit or output neuron. There's only one output unit that makes it a new artificial neuron. A single neuron still can do powerful things in terms of crunching data. And that's what you see from the class demo and from the homework. By implementing Adaline model, or better, by implementing logistic regression, you can achieve 92% of accuracy compared to the baseline accuracy level, which is, I think it's 78% in the churn data set. So you can improve from 78% to 92 by simply using this. And the trick that is being played here is as long as the separation of the target levels can be done linearly. If it's linearly separable, how do I say that? linear separable doesn't mean it's simple. It's still complex. And if there are multiple variables, more than 3, we don't even have a way to visualize it. But by using a very simple example, if we have an example where we have 2 input variables, 2 columns, so we have x1 and x2, and we're dealing with a binary classification problem. If the cases are linearly separable by using the 2D scatter plot, we have 2 variables and 2 types of output label or target label is circle and dot. If things can be separated by a linear line, or even if there's some points that are considered biased, but if the model can do a pretty good job in separating the majority of them to achieve an accuracy that is, over 92%, then you can say that it's almost linearly separable. And the model is leveraging the linear relationships between each of the input with y. Together, the model can use a line, a linear line to separate the cases. This is considered linearly separable. What is not linearly separable? Oh, this is hard. Let me change a pen. So imagine that we have a curve going on. A lot of the points go into the dot, but there are a lot of dots around them. This is not really linear. Well, yeah, this is not linear separable. If you go this way, you'll miss these points. If you go this way, you'll miss those points. So you can't simply use a linear line. You have to use a curve to separate them cleanly. So this is more complex. It doesn't mean that you can't use a single neuron to do that, but you have to do feature engineering. You have to create quadratic terms to simulate, to emulate the curve. And it's not guaranteed that you can do that, right? So this is a limit. This is almost the limit of a single neuron. So single neuron can only do simple tasks that are linearly separable. If tasks are more complex, if they are not linearly separable, if the separation plane, multidimensional space, if the separation plane is so complex, single neuron will not do it. We'll talk about intuition later because we don't have much time today. And, oh, great, I have a very convenient tool here. Multi-layer perceptron is the beginning of the true artificial intelligence, I think. It tries to tackle the complex problems by trying to use computers to emulate how brains work. The brains work, how does brain work? The brain learns. We're not born with knowing how to deal with things. We learn over time. So that's a key part. Conventional intelligence models or intelligence machines, they have explicit rules. They are told what to do given a situation. If the situation changes, the whole system has to be redesigned by revising those explicit rules. They don't work well, even though, in the 60s, they could do something, but later on, I think Jeopardy, the IBM Watson that beat the human players on Jeopardy game, that is based on the conventional form of intelligent machine. It's based on a long list of if-else conditions as a hierarchical rule deduction machine. So that goes well for less complex, but tasks that require a large memory space as well as quick computation. That machine can do well, but not anymore. Modern intelligent machines rely on neural network as a basis. So that's why this is sort of one of the most important components of your program, your degree program. Without understanding, without being able to explain what happens inside the neural network, sort of the opening the black box. Without being able to do that, you are not getting the gist of the foundation of BizAN, which is the machine learning or artificial intelligence. So that's why. Human brains have billions of neurons. Fairly recent, 10 years ago, fairly recent science articles estimated this number. Scientists always suspect that there are 100 billion. Turns out to be, the best estimate is 86 billion. Not bad, but once you go into the depths, there are different types of neurons. There are other kinds of cells in the brain. So it's not only these, there are intricate kinds. We'll not talk about the details. Refer to this article. This is posted on Blackboard. Refer to this if you are interested. Another feature is that the neural chain is very long. Sometimes it's long, sometimes it's short, but a lot of them are long, and they form webs. That is the part that inspires the artificial intelligence scientists, the typical layout of, or like a prototype layout for the neural chain. This is I think it's a, what's the word? It has lost on me. So in medical science, this is an image that they produced, an image of the interconnected neuron webs. And also there are different kinds. So this is not only the same kind. So inspired by these, I guess the neural network is born. But having the foundation of the single neurons is much easier to do this. So let me unfold the process, sort of talk about the intuition of how do you connect single neurons into a neural network model. Turns out it's not as complex. There are a couple math challenges here, but then I guess that's it. And also the other thing that changes a lot from the implementation point of view, from logistic regression to neural network, is that it's much easier to have a bug when you program the implementation. That's the most significant challenge that you probably will face, is that when you do the homework, everything goes well, but in the end, your model suffers. The model should do as good as a baseline accuracy level. If it's a binary classification, and if there are two labels, label 1 is 90%, label 0 has 10%, it is 10% of the data set, then the baseline performance is 90%. You expect any model to do as good as 90%. If it's below 90%, the situation is that it's not the model's problem, it's the implementation's problem. There's something wrong during the implementation process that leads to the calculation, deviation of the calculation. It's not learning the way that's supposed to learn. it's making mistakes because of a syntax error, even though it doesn't give you an exception, even though it doesn't report the error. You know, during math calculation, computer doesn't monitor if the process is correct. It only gives you syntax error. But if your code mess up with something that leads to a deviated calculation, computer won't be able to tell, only you can tell. So by the end, when you calculate the accuracy, if you get an accuracy of 50%, that's a flashing sign. It should be at least 90%. Why? Because if you have a model that predicts every outcome in a test set to be 1, you have a 90% accuracy. You know, you're making all false positive mistakes, but as far as accuracy goes, it doesn't matter. So even the simplest model will be able to make 90% accuracy. So if you get something like that, you should check your codes. Wait, now how do you connect a single neuron into a neural web? I hope that this animation will be able to kind of explain it at the intuitive level. So let's look closely. This is the logistic regression, right? This model is logistic regression. How do you tell? Because the activation here is sigmoid function, and it squeezes the values into 0 and 1. So that's logistic regression. Everything else is the same as the Adaline model, right? So we have 2 layers. I said, you know, if you cut it, it's not really here. If you cut it here, this is input, this is output layer, and within the output layer, there's only 1 unit. Everything here happens in the 1 unit. So that's the background. Now here it's kind of mixing things together. These weights are basically describing the lines, the connections here. So let me get rid of that and just show you a clean input layer. This is the input layer, and there are connections between each input and each of the next layer. We'll talk about that soon. As for the output, I'll just treat it as here. The output values here, this is the output of the model, and that remains the same. Whichever model you use, you have an output. So same output. And imagine that we have an output layer here, but instead of having only 1 unit, we'll relax the assumption that it can only handle binary classification. We assume that it can handle a classification problem with total number of labels as T. That's why it can have up to T units in the output layer. So this is the output layer. And what happens inside, these are actually in the output unit, but let's replace that. Let's add something here. And that something, you can think of it as another output unit, but now because it's between input and output, it's not output anymore, it's hidden. But still, the way it works is it goes almost exactly the same as the output unit. So there's no fundamental differences, just because of the change of location. It's not. But here, instead of having 1, I can have multiple of these. Each of these work in the same mechanism as the output unit before, in terms of logistic regression. I can have multiple, I can have even more. I use the K to index the positions, and D would be the number of units here in a hidden. Now we can declare this is a hidden. You can give it a second name, or this is second layer. This is invisible layer. Same thing. It's just a label. It's a hidden layer. But if we can add more units here, we can also add one more layer, right? So imagine that this is input. Now this is input. Imagine that this is input. After the net input and activation, these now become can take the role as if they are the input layer. Even though it's not input, I add another layer. So now we can say this is hidden layer 1, hidden layer 2, the input and the output. Now it becomes more complex. Even with a complex structure, let me use a color that is easier to see. Okay. Even if it's a complex structure, if you focus your attention only on these parts, you have two layers. You have one layer, and every node of that layer is connected to one node in the next layer. Doesn't this look like a logistic regression? Right? So you can use this perspective to look at every unit considering the previous layer. It's a logistic regression. And the way forward propagation goes is exactly the same as a logistic regression. So this is why logistic regression is the building block. Any questions about what I say? Is there anything that doesn't make sense? So everything makes sense. Great. Now move on. Now you have better understanding of what a network layer, neural network is, and we are talking about MLP. What I showed you is a sort of an MLP that's taken to pieces by layers. Multiple layers. Every layer has a similar template. It just differs by the number of units in that layer. An output layer is a little special. It has to conform to a specific number, which corresponds to the number of labels in your target variable, right? And hidden layer is much more flexible. Let's do a quick read of how neural networks are described. You probably have read a lot about neural networks elsewhere before coming to this class, and this is what I do whenever I see a news or maybe a discussion or an article about neural networks. If it's not, particularly related to a specific algorithm that I need to look into, particularly in trying to implement that, I won't pay too much attention to the descriptions of neural network. So it's as if I know what it means. It can be a lot of different shapes. It can be a lot of different layouts, or it can even have different names. But neural network is a neural network. I typically would skip, reading those parts and going to the application part. But if you pay a lot of attention to how they are described, and if you have, read about neural network and a version of description that is very fun, and make sure to share with us, because as I look around, most of these descriptions are very similar to each other although not literally similar or the same, but they basically talk about the structure of the neural network. And because the structure has a common template, description don't vary a lot. But again, you can see some funny things that will cheer you up. So neural networks is a supervised learning system built of a large number of simple elements. These simple elements are the single neurons, each of the neurons inside, which is also called perceptrons. This makes sense, right? And then this conforms to what we have learned so far. Let's see. At first look, neural networks may seem like a black box. Yeah, somebody called it a black box, right? And I remind you that no more. It's not a black box anymore to you, to whoever is trying to know what a neural network is and how that works. It may seem like it's a black box. And the black box is mostly referring to the hidden layer or hidden layers. The input and the output layers are quite straightforward and quite understandable, right? Briefly, it's funny, when it says briefly, it has 4 lines and it's much longer than any other definitions. So isn't that ironic? Briefly, blah, 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 blah. Briefly, a neural network is defined as a computing system that consists of a number of simple but highly interconnected elements, neurons. They are organized in layers which process information using dynamic state responses to external inputs. Dynamic state probably means activations, because the activation functions are not linear typically. So, it's a step function of nonlinear firing of the responses to the inputs. So that makes sense. After learning what you have learned so far, this makes much more sense. Otherwise, it may read like just gibberish. Another one, neural networks are algorithms inspired from biological structure and functioning of a brain to aid machines with intelligence. That's much better. That's talking about something at least, right? It's not only it's not describing the structure, because even if you do, people generally don't understand what that means. What does it mean? Dynamic state responses means nothing to an average person, I guess. More. Neural network is a series of algorithms. They are algorithms, yes, that endeavor to recognize underlying relationships in a set of data through a process that mimics the way human brain operates. That's interesting. That's a pretty good attempt to summarize. Neural networks consist of neurons that pass a message or signal to other neurons based on the received input from, and form a complex network that learns with some feedback mechanism. It's not as good. I don't like this one. It's not as clear. Neural networks generate the best possible result without needing to redesign the output criteria. So this may not read like meaningful, because it's not trying to summarize using simple terms the layout of the structure. It didn't also even talk about biological structure of the human brains. But what it says is a key feature of the intelligent models, such as neural networks, that is different from the deductive rules or inductive rules, whatever way it is, of the conventional or previous version of intelligent machines. And the difference is that the model learns by itself. And this is probably why we call it a black box. the model learns patterns from the data without you having to tell it. What you have to do is make sure the data is cleaned properly, is pre-processed. It conforms to the way that the neural network model handles the data set, and carefully examine the implementation, make sure there's no missed steps or messed up alignment. The data and the structure need to be aligned. And that's it. So after that, the job is given to the neural network. Given good training and evaluation, it gives you good predictions, but it doesn't tell you like how, or it gives you a sense of confidence. Yes, you can get the confidence level of the prediction, which is the log likelihood, or the likelihood of the predicting a label. You can get that. That's good. But given two likelihood, given two predictions that have very different input variables, but still they have same level of likelihood. So the prediction is exactly the same, but the way the model predict these two input cases are different. The model doesn't tell you how they are different. So that's why perhaps it's a black box. We have one last one. To sum up, artificial neural networks are basically simulated brains. Now, I like this one best. Given everything that we had, and if we begin with this one, it's also pretty fun. Which one do you like the most? Is there a winner, do you think? Is there one of these? Is one of these the best? Definitely the best one that make all the other descriptions or definitions shy away? What do you think?
I like the top one there.
The top one on this slide?
Yeah, on this slide. But I also like in the second one how it mentions about the feedback mechanism. I think that's pretty important.
Oh, okay. Yeah.
A mix of those.
Right. Yeah. So would you give up everything else for one of these?
I can't remember what was on the other slide.
But well, yeah, it's kind of long. But let's say we only have 4. Would you give up all the others and just leave one? And
probably the top one, because when it says human brain operates, it that's a feedback mechanism, I think.
Which one? The first one. Yeah. But I like the last one a lot, even though it may not be the best, but sometimes less is more. But anyway, not a single one of these summarize all that is essential here. It just describes from different perspectives. And I guess this is why it's a black box. You have thousands of interpretations, even with the basic version of the neural network, which is MLP. Even with that, you have hundreds of ways to interpret that. It may seem very fascinating at the beginning. Once you are very experienced, you look at these and you have no feeling, because you know what's going on behind it. None of these summarize the whole picture, and only you knows what's going on. But again, over time, you'll kind of appreciate the fascinating aspects of the way people describe it. Then you reconnect with these interpretations and with the model, which is sitting in a computer. It makes people exciting. That's what's fascinating to me. So I guess we don't need to do a breakout room. This is more of a, what do you feel about neural networks? So For the rest of the module, basically, I use a prototype model of the MLP. So we assume 3 layers. And the only difference between this MLP and logistic regression are 2 things, basically. In terms of the structure, we have a hidden layer. That's the most significant difference. We have a hidden layer here. And in the output layer, there are more than one unit, because we want to relax the constraint. Sometimes we have multi-label categorical variable as a target, and we want to be able to model using the same codes to be able to model the problem with more than 2 labels, right? So with 2 labels, you can use 2 output units. You could also use 1 output unit. That does, the inner workings are different, but the outcome, the result is almost, is you can say it's the same, because the result will be the same. It's just the format is different. With 2 labels in the target, if you use 2 output units, you're kind of wasting one of these, because the knowledge of one infers the knowledge of the other, right? But this makes it easier to scale up, to have a target variable that's multi-label. We have 1 input layer here, works exactly the same. I like to use J to index it, and the number dimension is M. There's only 1 hidden layer for now, the prototype. I like to use K to index a particular unit in the hidden, and Y, and the total number of units in the hidden layer is D. YD, because it's hidden, and D is not being used by any other notation. In the output layer, I like to use L, and the total number of units is T. And this T is the same as the number of labels in the target variable. So, the input layer, the hidden layer, is the only thing that you can change D freely, given a problem. You can decide D cannot be 0, of course. D cannot be negative. Other than that, any other integer can do, but you will not have a super large number, because you'll definitely have overfitting. But anyway, D doesn't have too much of a constraint. M has to be the same as the number of columns in the pre-processed input data. It has to be the same. And T has to be the same as the number of labels in the target. And that has to be, right? That's the 2. And YT, because it's output layer. Easier to remember. What else? And so put it together, you have 3 layers. That's it. So this is the, and also 2 things marked in gray and with different font denoting 1. This is the bias term, and the bias that goes into every net input is a standalone bias factor coefficient. There are cheat sheets, same tools, but different layout because of the different model. This shows you that the backprop of the neural network is much more complex as compared to a forward prop. Forward prop, you can do it in 1 step. Given a function, you can define a custom function. The backprop has at least 4 stages, And these 4 stages, each of these have substages and substeps. That's how, you know, how much more complex it is. But don't worry, you can do that. And with notations, you can find all of these in on Blackboard. This picture is cut off because it's too long. But you can print them out. They are still readable. And in the video, or later on, you know, in the next few weeks, when I talk about these steps, I'll refer to these cheat sheet process. So I'll briefly talk about these forward prop, but not talk about backward prop. But the general mentality is forward prop is going from left to right, because left side is more is closer to the input layer. It's the upstream of the information flow. It goes to the right. The right side is the output. When you do back prop, you go from the output to the input. I mean, you go from the output to the hidden, then you stop there. There's nothing to do for the input, right? Then that's one loop. After that, the weights are updated. Then to make predictions and calculate performance inside this epoch, you will do one more time for the forward prop, but this time it's not repeating the same thing. It's repeating the same procedure, but it's different calculation because you have new weights. You have the same input, but now you have the weights. Weights are updated, weights and biases. So the prediction, the forward prop, is supposed to be better. It's more accurate this time after the weight is updated. In terms of just a quick overview of the steps, where is the, see that? In terms of, so we will do the initialization. Make sure you have all the, you know, the weight matrices initialized, biases initialized. And this time we have to initialize everything because they are the placeholders. When we do the first time, when we do the first forward prop, we have to use all of those values. And now we get rid of the old weight, we directly replace the new weight. So every time the weight is replaced. So then we go into for loop. The first thing to do is the forward prop. And inside the forward prop, I normally say 4 steps. It's easier to remember. The first 2 steps are about the hidden layer. The second 2 steps are about the output layer. Right? So the first step, it's always net input first and then do the activation. And net input first and then do the activation. To refresh your minds, this is how logistic regression works. You have an input layer and a hidden layer, which is the output layer in the output unit in logistic regression. You first calculate the Z. So imagine this is one of the unit in the hidden. You calculate Z and do the activation, right? Do the activation. You get the phi, which is activated value, and that's already 2 steps. So if you have another unit in the hidden layer, again you calculate Z and then do the activation. Calculate phi. So if there are hidden layer is D. If there are D number of units in the hidden layer, then you'll do this for D times. But we don't do that. We don't do a loop again. We don't use another loop to loop through the D. We use the matrix notation. So for each of these D, let's say for the first unit, you get the input. For the first D, for the entire input data, it's n by m. M is the number of columns of the input data. M by m. And for this unit, you have how many weights? The number of weights is the same as the number of dimension of the data. So for this unit, you have m lines connecting the m input units. So for this Z, let's see, for this guy, only for this guy, the weight of the hidden, let's say hidden 1, this weight is a vector because it's only for that unit only. It's a vector. It's like a logistic regression, right? The weight is a vector. This factor is multiplied by this matrix, and it becomes a m by m, m by 1. It becomes a row, or it becomes a column. Becomes a column. So this Z activated value becomes a column. It's a vector. And by matrix notation, so it's like that. So this is hidden layer unit 1. After activation, you have a column. And you for the additional units in the hidden layer, you simply stack them side by side. By the end, you have D, right? You have D columns, not J, sorry. It's K. So in the end, you have N rows, D columns. The activated value in the hidden layer has a dimension of N by D. Very straightforward, easy to remember. The net input and the activated value of the hidden and output, regardless of which one of these, or regardless of which layer it is, the number of rows is always n. It corresponds to the sample size. What's different is the second dimension. It's the same as the dimension of that particular layer. So hopefully that helps you remember things, or I think this part you would have to remember, and it's not by hard memory, but it's by understanding it. If you understand it, you can derive this is a number that should be here. It helps you check your codes for any bugs. So that's a forward prop at the conceptual level. I think the next step is I think the next step, okay, the data set. The data set is the same as I used previously. It's a default tool, but this time I have already split them for X and Y, and I've already pre-processed them. So you don't have, so there's no need to pre-process that. If you follow the demo code, you can see that, and you can download the data. The data is now on Blackboard. The same case, and the only differences are the X variable has more columns because it's pre-processed. The values are already min-max normalized. The other major difference is the structure of the target, the Y data. It's now in one hot encoded format. It has 2 columns because there are 2 labels. And column 0 which flags the no default outcome, after one hot encoding, is ordered as the first column. And column 1 is ordered is put in the second column. This way corresponds to the index of the column label, makes it easier to convert the values later on. And so the plan is to go through and talk about the implementation of the forward problem. And I will stop here. We have a lot of time after the exam, so we can do that then. So I'll stop here. Now I'll talk about exam. So it's scheduled for next week, class time between 6 to 9. You may not need 3 hours. It's just, we have 3 hours for planning. But hopefully you don't need 3 hours, because that would be exhausting. It's not going to be super long exam, but I do, but it's hard for me to estimate how much time you will need. So I will kind of calculate an upper sort of, if suppose a student who's not very familiar and has to go through the materials, how much time will he need or she need? I will use that to kind of calculate or to plan for the number of questions. But because the data set is new, it's a new data set where you can use the same skills, but you will have to apply, judgment to adapt those to the new data set. And that is going to take some time, I think, right? Because for a new data set, you need time to understand it. You need time to explore it. And if you have a bug in your code, God forbid, that may eat a lot of your time. So, but for exam questions, I'll make it as straightforward as I can. No tricks. The topics are basically modules 1 and 2, both conceptual and the hands-on. I would say in terms of time, hands-on would take much more time to do than the conceptual, because conceptual is quite straightforward. It's open book, so you can use your resources, anything. You can print things out, it's fine. But during the whole time, it's individual exams, so no discussions. But we'll keep the Zoom meeting open. Anybody who doesn't join the meeting but finished homework will get 0, understandably. And also during the entire process that you're working on your exam, before you submit the exam, video has to be turned on. Anything else? No private chats, and that's it. The types of questions, you can imagine several types. Short answer for conceptual problems, or maybe also some of the steps in the hands-on require you to answer and interpret the results. That would be also the short answer questions. That's part of the hands-on. In terms of hands-on, I guess the major components are understanding the model, implementation, interpret the model, and also interpret the steps sometimes. Hypothesis testing is also a major part, but I think that's quite straightforward. And anything else would be related to data preprocessing, exploratory data analysis, or maybe doing some plot. But plot may or may not be here. Because plot tends to create bugs that is hard to solve, and it's not very essential. So I don't think that should be a big part. But if a plot is needed to plot the learning curve, then that plot is quite straightforward. You shouldn't have too much of a bug there. as long as you have trained the model successfully. So that should be, that's my plan. That's the overview. 7:20. Great. Now I'll open this time up for reviewing the exam. Now let me exit the share. So questions, the more specific, the better. For hands-on questions, if I can do a demo, that would be better. Any questions?
I have a question regarding the hypothesis thesis.
Yeah, go ahead.
Could you explain, please, what do you want to prove there? Because I understand that you're comparing the test data set versus the trained data set, but I don't clearly understand the conclusion. So what do you have to keep in mind when preparing your conclusion?
Okay, so there are two ways to kind of understand, you know, your perspective about this question. This question can be purely about understanding, you know, understanding the purpose of or the philosophy behind the hypothesis testing and how, you know, why is it useful here? That's one way to kind of interpret your question. The other is purely about the exam. How do I answer this question to get all the points? That's another way to interpret. So which one is it?
It's the first one.
Okay, okay, great. So that's the philosophy then. You know, hypothesis testing is hypothesis testing is sort of a good mechanism to see through the truth by looking at the data, which is sometimes noisy, right? So give you an example. Let's say that the purpose is to just, you know, exactly is to compare the proportion of the turners in the two sets, train and test set. And we know the sample size of each and the proportions, we can calculate the number for each set. Suppose that the first set returns proportion of 21.7. The second set returns the percentage as 21.2%. So they are different by 0.5%, right? In real life, you'll always have these differences, even if the two sets are very close. You have this variance because of random variation. So do you conclude, without hypothesis testing, do you conclude the two are different or the same? You know, how much same is the same? How much different is different? It's hard to make judgments, right? So because of this challenge, hypothesis testing provides a mechanism to do it more, you know, more scientifically. It's mostly relying on statistics, the knowledge about statistics. What troubles the situation, the task, which is comparing equal proportions, or to make a conclusion about equal or unequal proportions. What challenges it is the variation. And statistics is the science about variations, about randomness or variations. Hypothesis testing tells you at least a bottom line at which you can reject the null hypothesis. So it gives you, at least gives you a way to identify those situations where, you know, you're unlucky. You know, recall that the random split of the data set into train and set. Because of the random number generating mechanism, it almost always works, but you never guarantee it's 100% work, right? What if you're unlucky? You get into the 1% chance of getting a poorly split data set, and without hypothesis testing, you calculate the proportion, it's still close. There's no way to tell based on descriptive statistics. So you assume, yeah, the split is good. Then you go about and test the model. The model fails every time you use a test set, and you're exhausted. What can you do? So here in diagnosing what is wrong with the model, at least you can find out one reason. The split might not be good. If the split is not good, the fundamental structure of the variances inside two sets are different, then a model that's trained using one set, you cannot expect it to work well on the other set, which has, significant deviation in structural variances. So that's the reason. I know it's very long. I don't know if it makes sense.
Yeah, thank you, Professor Ma.
Yeah, well, anytime. All right. But also, coming back to the exam, you don't have to provide those reasons in your answer. It'll take an hour. That's not my expectation. The expectation is, how the video demos, or how the way the way the slides talk about. It's, it follows a procedure. It follows a format. As long as you follow that format. But I would say I would recommend that during exams, don't try to save a few words. Just make the sentence complete. Follow the procedures more closely to the slides, the procedure slides. Just just give me a clear reason to give you all the points. So that's what I expect. That make sense? Any other questions?
Yeah, so would you suggest the best way to prepare would be the 2 homework assignments and then the review?
Yeah.
Right.
I have a question for code.
Yeah. Go ahead.
I'm not sure what's mean one-hot encoder. What is this for?
One-hot encoder is to, I think you asked this question before, but somewhat related.
Okay.
I think it, let's see, let me use a blank slide. And
yes, also connecting to this one, like the use transformer for category variable for one-hot encoder. So
right.
why we need a transform for category variable?
Okay, I think I understand your question. So the reason it goes, it's quite fundamental. So it's good. So let's make the example of a categorical variable. This is one-hot encoding is related to the categorical most of the time. Sometimes we also use that on the target, but you understand that converting the target variable into one-hot encoding serves a different purpose. It's for the neural network model that we'll talk about when I talk about the implementation of neural networks. So wait until I talk about those. So far, one-hot encoding is mostly used to transform the categorical variable. So suppose we have a categorical variable. Can you give a very brief sort of interpretation of what is a categorical variable?
Like 1 or 2, like gender, female or male.
Mm-hmm. And remember that it can have much more labels. Not one or more, not 1 or 2. It cannot have one label. If it only has one label, the variable is not a variable. There's nothing that varies. So at least 2 possible labels, right? At least 2 positive labels, and so that's the binary. And gender is a good example. But as for gender, one high encoding is not always required. I'll talk about why in a second. It should become very clear by then. But let's use another example. This is the special case. Another example is marriage or marital status. And name 3 levels that might be possible that might be meaningful to this variable. It's, you know what M is. Yeah.
Yes.
M is married. What else?
S single.
S single. And what else? And okay, O is everything else.
Okay.
Make sense? We don't have to
Yes.
specifically talk about the other states. So there are 3 levels. Now, compare that to a numeric variable, which is age, is the most straightforward variable. Age goes from, for typical data set, goes from 18 to 80. Right? You can take any integer values in these. So the immediate difference, other than that there are fewer unique values here in categorical versus numerical, another difference is that these numbers are ordered. They are calculatable. You can, which means which means you can do arithmetic operations. Adding makes sense for age because it follows a linear pattern. Subtraction makes sense for age. Multiplication, I don't know, but generally it conforms to what we understand as a continuous number. That's age. For marital status, the first trouble is that this is text. Any algorithm, any machine learning algorithm doesn't work with text. In terms of the supervised learning algorithms, it cannot directly work with it. It doesn't mean that we can't model this. We have workarounds, right? So one-hot encoding is a workaround. It's the workaround for us to be able to model the effect of the relationship of marital status. So the text doesn't work well. Now we can put them into numbers. We can say married is 0. Let me use 0 as corresponding to other. Single is 1, married is 2. To label these values, just to convert it to numbers. Now then we include this marital status as if it's a number with like age. What might be the problem?
Yes, it cannot be doing any math.
Yeah, it's not even ordered. The order is arbitrary, right? This is kind of implying married is twice as good as single, but I guess someone here would say not really, and single is better than all the other. It's not really. Yeah, single is higher than the other, and other is a combination of everything else. So you cannot say that. So that's another problem, right? And also you cannot add, you cannot subtract. So you cannot add this as if it's a number. So what can we do? Something that will make sense is to convert it to a sort of a matrix. Convert this variable to a matrix instead of treating it as a single variable. In that matrix, we only have values 0 and 1. And we have as many columns as the number of labels. So we have married, we have single, we have other. So a variable suddenly becomes 3 variables, but this is the, you know, the cost that we have to bear with, because at least it provides a workable solution without increasing the number of columns too much. Let's say that we have, this is customer, let's say. So I denote a particular customer. For this customer, his or her marriage status is M, is married. So we can say, you know, this person is married, but not really the other 2. For another customer, that's single, but not, you know, it's just checking things off. And sorry, where does the circle come in? Every row has to have one and only one check mark, because it has to map to the original data, right? And you can imagine for the, for the rest of the data, check mark is, there's only one, and there's one and only one, has to be one check mark in all of these columns, and everything else has to be cross. This makes sense, right?
Yes.
And now the only trick to do is to convert check marks to 1, value 1, and to convert the crosses to value 0. And after that, what you have is 3 columns of zeros and ones. You know. Let's see. So we can include all 3 variables. In fact, we can only include 2 of these because of multicollinearity. But let's just imagine that we include all of these. It does the job of including the variances in this variable without introducing the other problems. The reason is when the model reads the data and try to process the data, which is in the net input, right? In the net input, you have the weight, and there's a weight coefficient corresponding to each column of the input data. That's Z. You know, we have the Z is the X, and W, J is the J goes from 1 to M. It's the weighted sum of all the input variables. For this person, for the marital status variable, it has to consider multiple columns, the flag columns. So for this person, only this weight will make a difference. It will be multiplied by 1, which is the flag, right? This person is married, so this married column will make an effect. It will be calculated, it will be multiplied by the weight and included in the net input. Here, even though the weight is not 0, the flag variable says these are 0, so these will not make an effect. So for this person, by including marital status in this way, you will make sure that the weight will capture any effect, if it's significant, any effect of this category of the marital status if it's related to the target variable, right? So I think, you know, this is how I would explain, you know, why doing this, and hope that's clear. Let me know.
Yes, it makes sense more.
Great, great. But you know that when we do the one-hot encoding for the input, we have to drop the first column. So always remember that. And by the way, by specifying one-hot encoding and drop equal first, it will rank all the labels based on alphanumeric order M will go first, O will be the second, S will be the third, and M is the first label, it will be dropped. So in the end, you will have two columns only. You will have single and other. You know, if you have a question about why this won't affect how the data is, you know, is making an effect as this seems to be losing information, but not actually, because 2-0 here implies that this person is married. It can't be any other situation. So that's why. And including 3 of these actually will lead the model to be unstable because of collinear. All the 3 variables, the 3 columns here, if you consider them all together, they are collinear. It's in a way that one of these columns is collinear with the combination of the other column. It's still a collinear relationship. So that's why we have to drop one of these.
So,
Go
Sorry,
ahead.
that's what I was going to ask. Which one are you dropping?
You can drop anyone. It doesn't affect the model training. It only affects when you look at the coefficient. The way you interpret that coefficient has to be bounded with a label. So that's the only effect. That makes sense?
Professor Ma, is this the same thing as we did in homework 1?
Yes.
There's a question that asks us to do the flag variables and we need to drop one.
Yes, yes. This is exactly the same thing.
but the flag variable is only 2 or can be more?
Oh, yeah, you know, flag. Okay, let's see. Let me clarify that. Pen, yeah, blue. So what's a flag? A flag is a column, one column, like this. This is the one column. This is the one column that only has values 0 or 1. And what this does basically is to flag, that's why it's a flag variable. It's flagging the occurrence of a situation, right? This column is flagging whether or not this person is male. In the case this column is 1, it's definitely saying that this person is 1 and we know the full information. However, if this column is 0, but there are multiple other columns, you are not sure which one of the other labels that this person definitely is, but it's definitely not male. So that's what a flag variable does. When it's 1, information is complete. When it's 0, information may not be complete. That's what a flag variable does. Now, I also said there are binary, right? I think these two might be confused. A binary variable simply means there are 2 labels. It can be in text. So, you know, male and female is a binary. You can think of other examples, but that's binary. In order to include a binary, you convert that into one flag variable. That's both, in case of the, you know, the special categorical variable case, a binary variable is naturally, sometimes it's already encoded as 0 or 1. So it's already a flag variable, but other times it's not if it has numeric labels. Or sometimes it's encoded as 1, 2, which you have to do some conversion. You know, it's not the best practice, even though it may cause too much harm. But if it's coded 1 or 2, you have to convert it to a flag, which has only 1 and 0. So that's one way to understand it. The other way is that you can think of binary as just another example of categorical, right? By having 2 labels, you have 2 columns. But since you will need to drop one of these, you end up with 1 column. And that's why it still has only 1 flag column for a binary variable. I hope this clarifies the difference as well as the similarity here.
So can I make sure, so binary is the two neighbors like gender, but the flag is 0, 1 is like the input values, right?
Yeah, yeah,
Okay.
yeah.
Okay.
Flag variables can be readily included in the model, can be trained. Binary doesn't have to be. And sometimes it's already in flag format. You need to look at the data, right? Other times it may not be. It may be in a text, which is entirely not usable. You have to convert it to flag. And other times it's using other codes than 0 and 1. And what if it used 0 and 1 and -1? It's not ready yet. So by a simple conversion, you can convert it to flag. Yeah, makes sense?
Yes.
Great. Any codes that I need to demonstrate here, or maybe not? The codes may be straightforward. It's a concept that may be luring. Yeah.
I also have a question, like why weight can be negative?
Weight? You mean weight?
Yeah.
Why can weight be negative?
Yeah.
All right. I think let's see. I need to go to a different slide. Why can so what is a weight then? I think let's forget about neural network. The concept is the same in terms of regression. What is a weight? It is a way to sort of describe the influence of one variable to the target. That makes sense?
Yes.
If this weight is for the variable age, right? We typically multiply the weight with age. And whether or not the weight is positive or negative or maybe even 0, it can be 0 or very close to 0, assuming the data is standardized. The weight will tell you two things: whether or not the age variable is significantly related to the target, and two, whether how age is related to the target. If the target is, I don't know, can you think of an interesting example that may be affected by age?
Like income.
Income? Yeah, generally, more senior professionals earn more, yeah, higher in rank. So let's say, yeah, income. For income, age has a positive. W tend to be positive because the connections, the associations between age and income is positive. But I guess we need a second example. Age and, okay, I have a very good example. No, it's bad. It's in the same direction. Never mind. Health, maybe. Okay, so this is health. This is, or you can say disease. Not disease, it's health. It's the opposite side of disease. It's the, you can say stamina, your energy, things like that. Things that only young people have. What else? Naiveness, maybe, I don't know. Things that only young people have. So let's say the target is health, and you can think of anything, lack of any, cancer or lack of any other conditions, hyperpressure, things like hypertension. As people age, we tend to have poor health. That makes sense?
Yes.
So for that relationship, W will be negative because the larger the value of age, you know, it's 70 versus 17. The larger the age multiplied by a negative coefficient, the health will become more negative, which makes sense, right? So for here, a negative coefficient makes sense. So that's why it can be negative.
So can I understand like negative, this means like bring negative effect to the targets?
Yes, yes.
Okay.
In terms of, and the positive and negative describes it's really the correlation. But in terms of the impact, it's the direction it's the direction of the impact. Sort of it's you know, it tends to, I mean, it's hard to say. How can I say it? Somebody can help? You know, what does negative coefficient means? In terms of negative effect, it means decreasing the value, but it doesn't say anything about the strength. You know, and a coefficient can be negative, but it's almost zero. You know, minus 0.0001. This coefficient is negative, but it almost doesn't have any effect because it's so small. It makes no impact at all, realistically. As versus if a weight is -2, it's very powerful, -2 in terms of standardized inputs. That means it has a high negative correlation between the input and the target. If the input changes, if the input increases, the target will decrease sharply. That's what it means. Does that make sense?
Yeah, yes.
Great.
Thank you.
Yeah. Anything else? Dan, did you say you have a question about the codes, or does it need a demonstration?
It's just a basic question, like.
So it's the categorical, and so it's about this.
Yes,
So
and I also want can like in exam for logistic regression model, for when we're doing the activation function, we always put a 250 and a 250 for A max and A min.
Oh, you're talking about the clip?
The signal, yes.
The part of the clip, right? That part is actually, it's just there to make sure. Oh no, this is today's. The clip part of the code. Hold on. Let me bring up the file. I'll stop share for a moment. But okay. Let me get the homework 1, right?
2.
Homework 2.
Yes.
Yeah. Logistic regression. So let me get the logistic regression demo. Let's see. Oh, clip. Okay. Now let's share. Can you see this?
Yes.
So this is logistic regression, and the activation, sigmoid activation is in the it's the beginning of it's a forward prop. So in doing the activation, there's a clip step, do you know what this does? And then we'll help explain what these two are.
Can you explain again?
Yeah. So what it does, it, Z is a matrix, but well, I think Z is a vector here, but it doesn't matter. NumPy apply the function to every element of that. So we can imagine Z is a single number for now. So in that case, clip. Given a Z, let's say Z is 10. Typically, it's not very large. What clip does is that it takes that number and it compares with, this is Z, compares with two extreme values. Minus 250 is the number that we specify. It can be any number you choose, but they are chosen for a purpose. It compares the value, all the values between minus 250 and plus 250. If the value is between these two, it does nothing. It returns 2. But if the value is in these gray region, it will return the bound. If it's below minus 250, it will return 250. So in a way, it's cutting off the extreme values, right? So if Z is 300, then clip of Z will return 250 because it's too large. The purpose of doing this is we don't want the function, we don't want the values that is to be taken an exponential here. We're taking an exponential function. We don't want this exponent to be the power component to be too large. If it's too large, this function takes a lot of time to calculate. But in the logistic regression, we almost always never will even need that big of a value. The input value, at most, it will be between minus 10 and plus 10, right? So we use a number that's large enough to cut off any extreme values to just save some computation power. And this is rarely used even. I think in most of the calculations, this function is not doing anything. It's not altering the values, but just in case we have an unlucky random start, right? The starting point is random. So we can get unlucky. In case we're unlucky, we want to cut off a very large values just to save the computation power in that situation. So that's the only thing it does here. And why these values, what these two values are doing, it's the extreme level that you specify, right? You can do minus 100, plus 100, and it's almost the same effect. But, I said the most values will lie between minus 10 and plus 10. Why do we not use these? These are just common cases, but we may have a data that's more difficult, and we may have to exceed these common bounds. It's not unusual. It's not typical, but it's not unusual. We want to allow that, so we choose values that are large enough. So the A min is the minimal, is the lower threshold. The A max is the upper threshold. We want to cut off the extreme values. I hope that makes sense.
Yeah, yes.
Yeah, and after that, you simply plug in this Z clip into this is the sigmoid function, right?
Yes.
Anything else?
So why is a 1 point? Can we just put a 1?
This is a programming convention. Sometimes we may have Z clip as, it's very rare, but what if you're playing with a very simple data set you simulated? Maybe it only has 3 rows. With 3 rows, you can still test your code, right? And in that case, the data may not be in floating point. We want things to be all in floating point. So in case, you know, I modify the code, in case the Z clip has values that are all integers, and somehow maybe taking the exponential returns another integer, maybe, and then +1 is integer, integer divided by integer, it may cause some trouble in terms of the programming. I mean, it may be confused and return an integer by rounding the numbers. We don't want that to happen. So we put the period indicating this is a float, even though it's 1 point, meaning this is a floating point. If any part of the calculation has a floating point, the programming will assume the result should be floating point. So it will avoid those cases. That's the only reason we do that. It seems like ridiculous, but that's a pitfall of programming.
Okay, thank you.
But even if you forget this, you won't be penalized. That's the bottom line.
Oh, we
You have
will
to-
get
Yeah,
into.
it's not critical. It's a better programming skill,
Okay.
but it doesn't. Yeah, it's not core part of this course, definitely. But I guess if you understand this and to save the point, then you won't even do that, because a better programming habit probably care more than, you know, saving the just little time, right? It's only when you don't understand the code and you end up typing, I think in one of the students' homework, it ends up to be this. It makes everything different. Trust me, because of this one typo, it made everything different. And this typo is understandable because the period is just by the side of the slash. But changing the period to slash means this is doing a division plus. So it changed the calculation significantly, and the results are totally messed. So be careful with those.
Okay.
Yeah. Anything else? We're good on time. Any other questions? No more questions? You can always email me if you think of questions. And I think I'll finish grading homework 2 by this week so that you can take a look and, you know, prepare. If there's any, you know, mistakes, then you can correct them. Anything else? All right, I'm glad to see everybody's prepared. I know that doesn't mean that. You probably never get to that, but just let me know.
I'm sorry, I have a last question.
Go ahead.
Just I just want to know what's the slope of a gradient is a cost?
You mean the
slope.
meaning of gradient?
Yeah, the slope of a gradient. I mean the slope.
Yeah, gradient and slope. Gradient is a critical piece of information that can help you reduce the cost. You know, the gradient is the slope of cost. That's the exact relationship, right? You have a cost curve, but then the slope is that gradient. So that's the relationship between the two.
Okay, that's all. Thank you so much.
Yeah. No. So one last time, let me ask you, any other questions? Now we can call it a day. Oh, let me stop the sharing for now. Yeah, we can call it a day. Now let's do that. Enjoy the rest of the evening. And anytime, let me know if you have any questions. So meeting will be stopped. Enjoy your night.